Welcome everyone to this presentation about our paper, Learnings from a Retail Recommender System on Billions of Interactions at Bol.com. My name is Barry Kersberger and I present the work done together with Sebastian Schelte. This research is part of Ahold Delhaize Research, AI in Retail Lab and the University of Amsterdam. Today's internet users face with an ever-increasing amount of information, and this situation has triggered the development of recommender systems, intelligent filters that learn about the user's preferences and suggest relevant information for them. With rapidly growing data sizes, the predictive performance, the processing efficiency and the scalability of the machine learning-based recommender systems and their underlying computations becomes a major concern. In our paper, we describe the architecture of a real-world recommender system called Abo for Bol.com, the largest online e-commerce platform in the Netherlands, which handles billions of interactions of several dozens of millions of items every day. The Abo, Ander bekeken ook, which is Dutch for others also viewed, recommendations are shown on a product detail page to enable customers to discover other products that are relevant to them, such as different versions of the same product, similar products, and products that are complementary to the displayed item. We conducted 2 studies on enhancing the predictive performance of this system with both algorithmic and system-related approaches. We will first describe our current recommender system called Abo. Abo is designed for distributed computation and implemented on top of Apache Spark. All of our components are loosely coupled, so they can run independently from each other while exchanging data via a distributed file system. Our architecture consists of a batch system that is responsible for executing the data-intensive model training workloads offline on a 18 billion user item interactions, which is about 3.5 terabytes in size. We periodically pre-compute the recommendations for every item in the catalog, typically once per day for all the 70 million products, which takes about 2 hours to execute the full job and store the predictions in the database. In the candidate component, it determines which data needs to be fetched from which database BigQuery data source, and subsequently collects, cleans and filters the data. And next, it executes 9 nearest neighbor-based recommender models that each generate a list of recommendations for products in the catalog. The ensembling component aggregates the output of all 9 recommender models to generate a final set of recommendations per item in the catalog and applies a set of manually defined business-specific filters to the recommendations. These filters remove potentially unwanted recommendations such as combinations of adult with non-adult products. The Avalanche component handles the bulk update of the pre-computed recommendations into the Bigtable database. It is implemented on top of Apache Beam and it converts the recommendations to a protobuf format with a fixed amount of recommended products to guarantee a fast deserialization at serving time. In e-commerce sites, there is typically a hard service level agreement for response latencies of internal services. And in order to adhere to this latency service level agreement, the recommendations must be inserted into the database without raising the CPU load of the Bigtable database too much. This is challenging when inserting a large set of recommendations in the table because the CPU load varies during the day and of course while rating the data. The Avalanche component will automatically adjust its insert rate into Bigtable, and we address this issue by sharing the responsibility of maintaining a low Bigtable CPU load with the Avalanche job. We add a rate limiting mechanism to control the insert rate of Avalanche described in algorithm 1 in our paper, where we aim for an average CPU load of 35% in the Bigtable nodes. And the online serving system is responsible to serve the recommendations online with low latency using Google Bigtable as a fast database. In recent years, the neural networks have drastically outperformed traditional machine learning models in various domains. It's therefore a natural question to explore the benefits of neural network approaches in comparison to nearest neighbor approaches such as our system. In contrast to academic studies, we have to look at additional dimensions, such as the scalability and training costs, in order to judge whether it would make sense to deploy a neural-based approach. The academic setup that is closest to our production use case is the session-based recommendations, where the goal is to predict the next item or set of items that a user will interact with, given the current items of her session on e-commerce datasets. Interesting recent academic research indicates that neural-based approaches do not outperform classical nearest neighbor-based approaches in this scenario. In study 1, we replicate a prominent study from Janak and Ludovic on a sample of our production data to evaluate whether it would be beneficial to invest the scalability and training for neural networks. We use real-world clickstream data from our e-commerce platform for our study. We create 5 samples, each spanning 31 days from different times of year in order to minimize the impact of seasonal effects. We bin users by the amount of purchases that they made, and we apply stratified sampling based on these bins to select a set of sessions that represents the activities of a wide range of customers. Each training dataset contains around 1.2 million user item interactions and about 100,000 distinct items in each sample. Hyperparameter optimization for neural-based recommendation methods can be very time-consuming, even on small data. We therefore apply the following approach to tune the hyperparameter for all methods. We explore 100 combinations of hyperparameters in random search on a data subset of 100,000 user item interactions, and we select the hyperparameters that result in the best mean reciprocal rank at 20. We schedule runs on different machines in the Google Cloud to retrieve the results in a reasonable time, even when allowing the methods to use the GPUs. Hyperparameter search for NARM took more than 6 days to compute, in contrast to less than 2 hours for the VSKNN approach. The metrics mean average precision, precision and recall evaluate to what extent an algorithm is able to predict the next items, which you can see in figure 2. Green represents the nearest neighbor approaches and red represents the neural network-based approaches. The mean reciprocal rank, MRR, evaluates to what extent an algorithm can predict the immediate next item in a session, which is the evaluation metric that the neural network-based algorithms have been designed for and optimized for. We find that the nearest neighbor approach VSKNN consistently outperforms all neural-based approaches and even provides higher evaluation score for the mean reciprocal rank at 20, the metric for which the neural-based approaches have been designed. ABO outperforms neural method STAMP in mean average precision and precision, as well as the association rule and sequential rules, even though it has not been designed or optimized for this academic task of session-based recommendations. The time to train the neural network-based approaches is at least an order of magnitude larger than the training time for the nearest neighbor-based approaches. Additionally, 2 out of 3 neural-based methods require much more time for inference than the nearest neighbor methods. The 90th percentile of the time needed for a prediction with GRU4RAC and NARM on a small dataset is already higher than 100 milliseconds. Our second study focuses on enhancing the predictive performance of this system via system-related approaches. Most research focuses on improving predictive performance of recommender system via algorithmic changes. And motivated by our production setup, we are interested in the impact of orthogonal system-related improvements. These are in general hard to study for academic researchers without access to real-world systems. Existing research indicates that artificially slowing down responses affects the acceptance of search engines, for example. So a question arising from our production setup is, do faster responses of our system lead to better business outcome? And this is difficult to study because one cannot artificially make a system faster. So as part of a bigger reorganization of infrastructure, we were in the fortunate position to migrate our serving component and its database from a proprietary data center to the Google Cloud platform. And this migration included several changes, such as having access to more recent hardware, upgrading the version of Java, the libraries that we use in our serving component, as well as rewriting the code for retrieving records from the database and serving them. So we were in the fortunate position to run this extensive experiment. We ran a large-scale study and conducted an online A/B test on more than 19 million sessions, where we conclude that identical recommendation systems served with different latencies, so 90th percentile on the data center was 32 milliseconds and in GCP was 50 milliseconds, we observe a more than 2% increase in important business-related metrics. We think this raises interesting research directions for improving the suitability of neural network-based recommender algorithms for production settings. We also think that the impact of response latency should be invested more thoroughly especially with regards to potential trade-offs in model pruning and precision lowering for neural-based methods. These techniques usually decrease the performance in offline evaluation, but their potential for reducing the latency could have a positive impact on the predictive performance in an online setting. So in this work, we focused on how to improve the predictive performance of a real-world recommender system with both algorithmic and system-related approaches. We confirmed the findings from a prominent study that the simple nearest neighbor-based approaches outperform modern neural network-based methods in session-based recommendations on e-commerce data. We additionally found that VSKNN is orders of magnitude faster to train than the neural network-based methods. And this is an important property for a production system that has to conduct regular retraining of their models and adhere to strict time constraints for that. Our second study indicates that reducing the response latency for serving has a significant impact on the acceptance of a recommender system in e-commerce. We A/B tested this impact on more than 19 million sessions, where we were able to give visitors a better experience by improving the serving latency, which resulted in a significant increase in business-relevant metrics. Based on these outcomes, we are now working on our next generation recommendation system for session-based recommendations to a full e-commerce workload. I want to thank you, and I wish you a nice day at the ICDE 2021.